In the first part, we just basically introduced the sensory receptors, and now we ended on in the last lecture on somatosensory first order neurons, talking about the functional significance of axon diameter. Larger diameter axons transmit information faster than smaller diameter, and larger diameter axons are more myelinated, allowing for saltatory conduction, and that speeds them up as well, speeds up the transmission. So in the cutaneous or subcutaneous areas, we have receptors that are encoding information that we're getting. So touch is either categorized as fine or coarse. Fine touch includes a variety of receptors and subsensations. So some of these you can know the names of the different receptor ends, but it's not one of the learning objectives, so you know what that means. The Meissner's corpuscles, you can see, and the hairs on your skin, you can see how they detect fine touch. Coarse touch is mediated through free nerve endings throughout the skin. So the difference being those individual receptors, they have specific types of endings that detect specific things. So when you look at that Pacinian corpuscle, you can see how it could detect pressure. The Ruffini endings, they detect stretch. The Meissner corpuscles, they detect fine touch. So cutaneous receptors respond to touch, pressure, vibration, stretch, noxious stimuli, and temperature. That's a good thing to know. The contribution of cutaneous receptors is primarily kinesthetic, responding to stretching or increasing pressure on the skin. So when we move through our range of motion, you are going to feel some stretching in the skin. When you lean against something or somebody touches you, you're going to feel increasing pressure on the skin. Or say you're wearing compression socks, you're going to feel increasing pressure on the skin and in the subcutaneous tissues as well. So the area of skin innervated by a single dorsal nerve root is called a dermatome. And we have talked about this briefly in other classes. Although the cutaneous receptors are not proprioceptors, the information they gather does contribute to our position sense. So we'll talk about the receptors that specifically are proprioceptors, but all the information we're getting from our skin, that contributes to our proprioception as well. Dermatomes are used to diagnose radiculopathy and to determine the sensory level affected by a spinal cord injury. For the limbs, the two distinct distributions of sensory innervation are peripheral nerve and dermatome. So this diagram from the book shows the difference between peripheral nerve distribution and dermatome distribution. There's obviously some overlap, but a lot of times the difference between the two is used in the diagnosis of radiculopathy and other issues involving sensory level. So the cutaneous receptor types, fine touch and vibration, are encoded by A beta axons. They have a small receptive field. They are highly discriminatory, and they're specialized receptor endings. So those are those Meissner's corpuscles and Merkel's discs and whatnot. They're highly discriminatory. They know exactly what kind of sensation they are recording, and they're sending it to your brain. Subcutaneous fine touch has a larger receptive field and is less discriminatory. So the fine touch and vibration that's what you can feel just, running your finger lightly along your skin. Subcutaneous fine touch is less discriminatory. So fine touch, you can feel it. Subcutaneous, it's like in the area, but you're not exactly sure where. Coarse touch is encoded by A delta and C fibers. And remember, we talked about the A delta and C fibers as being pain fibers, nociceptors. They can be. They're free nerve endings. They don't have specific receptor endings. So it's crudely localized. It's in this general area. So tickle and itch are transmitted by C fibers, by free nerve endings. So a lot of times tickle and itch, they're kind of uncomfortable sensations, so you can sort of think of it that way. The uncomfortable sensations go more with the C fibers. And if they get extreme where it feels like a threat, then those are a nociceptive information. So A delta does crudely localized touch, and C fibers do tickle and itch. Nociceptive and temperature information encoded by A delta and C fibers are free nerve endings. So only A beta axons have those specific receptor endings, the specialized ones. C fibers and A deltas are all free nerve endings. So the axons that convey musculoskeletal sensory signals are classified using Roman numerals from 1 to 4. Isn't that annoying that there's different systems for everything, but there just is. Let's just be happy with that. There just is. So large afferents are type 1 and 2, and small afferents are types 3 and 4. Is this in the learning objectives? No. Do you have to know that specifically? No, you don't. All you have to know is the types of receptors. Not that they're 1s and 2s and 3s and 4s. So the muscle spindle, it's a 1A if you care. But it responds to muscle stretch and the rate of length change. So the muscle changes length, and the spindle sends a message to the spinal cord about muscle length and the rate of length change. The sensory endings of the spindle respond to quick stretches and prolonged stretches. Efferent messages that are sent back to the muscle to control muscle length change by contracting the ends of the intrafusal fibers. The center is non-contractile. So basically you get that sensation from the muscle spindle. The muscle spindle says to the brain, okay, the muscle is stretching really fast, and the brain says, oh my gosh, we need to contract the muscle in order to protect the joint. So these are sort of protective sensations, and we get that immediate efferent message to contract the muscle to protect it, basically, to protect it from tearing. So if you do a prolonged long stretch, you're not necessarily going to get that efferent response. So a quick stretch, you're probably not going to get a very good stretch because you're quickly contracting the muscle spindle, and the efferent message comes, contract the muscle and protect it. If you do a prolonged slow stretch, you will get more stretching of the muscle fibers. So that's something we can translate into day-to-day action in the clinic and in the gym. Golgi tendon organs respond to very slight changes in the tension of tendons. They respond to tension from active contraction and passive stretch. So our Golgi tendon organs are telling us a lot about what the muscles are doing. And they are 1B afferents, so a little slower than muscle fibers. They are, or than muscle spindles. And they are giving us information about joint position sense. So they are in the proprioceptor group. They're giving us a lot of good information. So the joint receptors respond to mechanical deformation of joint capsules and ligaments. So you can think of the Golgi tendon organs as being tendon proprioceptors, and the joint receptors as being ligament and joint capsule receptors. If you want to think of it that way, I think it makes sense. Hopefully it makes sense to you like it does to me. But the afferents that are associated with joint receptors are ligament receptors, which are the type 1B, Ruffini's, which Ruffini endings, they detect stretch. So they detect extremes of joint ranges. So extreme knee flexion or knee extension, we're stretching those Ruffini endings, and they are giving us information about our joint position. Free nerve endings, which are type 2s and 3s, are often stimulated by inflammation. So joint receptors being stimulated by inflammation That is largely the source of pain with arthritis. So people always talk about, this drives me crazy, but people always talk about, oh, bone on bone, bone on bone. Well, we don't have any sensation on the ends of our bones. We do have sensations in our joint receptors. So the pain from arthritis doesn't come from bones grinding on bones. It comes from inflammation and those inflammatory chemicals in our joint receptors. So proprioception is a combination of cutaneous receptors, Golgi tendon organs, muscle spindles, and joint receptors. So people with total joint replacements retain good joint proprioception in mid-range because joint receptors are not critical for proprioception. So the joint capsule is spared in a total joint replacement surgery, and they get a lot of information from that. So if that wasn't the case, then after total joint replacement, you probably wouldn't have any sensation and your balance would not be very good, you know. So it's really important to know, in the module, I have a chart, because, you know, I like charts, with all of these receptors and what they respond to. So that's what I want you to know, is what is the receptor, what information does the receptor send, and what stimulus does it respond to? So large diameter axons transmit information from specialized receptors in muscles, tendons, and joints. So these are our A-betas, our muscle spindles, our Golgi tendon organs. Medium-sized axons transmit information from joint capsules, muscle spindles, cutaneous touch, stretch, and pressure receptors. So there's overlap. The smallest diameter axons convey nociceptive and temperature information from both the musculoskeletal system and the skin, and crude touch information from the skin as well. So there's a lot of overlap between the function of the peripheral sensory axons, which is good, because overlap means if you lose one, the other one is taking up the slack, hopefully. Peripheral nerve lesions. So I always like to tie everything together clinically, give you a way to ground this information. So when you have a lesion of the peripheral nerve, neuropathy is a general term for dysfunction or pathology of one or more peripheral nerves. So neuropathy is a pretty vague, people will say, oh, I have peripheral neuropathy. It doesn't just mean one thing. It could mean just dysfunction of the nerve for metabolic or chemical or degenerative reasons. It could be complete severance of a peripheral nerve. So complete severance of a peripheral nerve results in the lack of sensation in that nerve distribution, in that peripheral nerve distribution. You might have pain, and you might have motor and reflex loss because of that loss of sensation. Sensory loss proceeds in the order of descending axon diameter. So first you lose the big ones. You lose conscious proprioception and light touch. Then you lose cold. Then you lose fast nociception. Then you lose heat. And then you lose slow nociception. So isn't that a bummer that you lose slow nociception last? So you can have no sensation in your feet except pain, which is, you know, not nice. But a lot of the sensation in our peripheral nerves is contributing to proprioception and position sense. And so if we don't have that, it makes it very difficult to walk and maintain our balance. Ataxia is, we'll talk more about this too in the cerebellar chapter, but ataxia is incoordination that's not due to weakness. So you have, your muscle strength is fine, but you're still unable to coordinate movements for whatever reason. There are 3 different types of ataxia: sensory ataxia, vestibular ataxia, and cerebellar ataxia. The Romberg test is used to distinguish between cerebellar ataxia and sensory ataxia. So basically, the Romberg test is a single leg stance, eyes open and eyes closed. If you close your eyes and you completely lose your balance, well, then it's probably sensory ataxia because you're you're not getting that input from your vision, you're depending on your peripheral sensation. Or your vestibular sensation is the other one. So the ataxia, because someone has ataxia doesn't mean they have a brain problem. It could be a peripheral problem. So if any place in the pathway isn't working, it's going to disrupt the function, if that makes sense, whether it's very distal or completely proximal. So stereognosis is the ability to use manipulation, touch, and proprioceptive information to identify an object. So this is what we use when it's dark and we forgot to turn on the porch light and we're standing on our front porch digging around in our backpack or our handbag for keys, and you're feeling everything with your fingers, you can't see it, and you're identifying that information. So stereognosis uses a lot of things. It uses that proprioceptive and touch information to tell you what's going on, but it also connects in with your memories and it associates it with different things. So if you had someone, let's just say you had someone in a society who doesn't have keys, they don't know what a key is or what its function is. If you put a key in a bag and had them touch it and identify it, they wouldn't say, oh, it's a key. They'd say, oh, it's a small metal object. It's sort of round on one end and pointy on one side or something like that. They could describe it, but they couldn't tell you what it was because they don't have that memory input. On the other hand, if you have more detailed memories about a particular object, you can identify it even more distinctly. Here, an example is when I was in school, we were doing, we didn't have test and measures lab when I was in school. We had it in other labs, but we were testing stereognosis, and somebody had put, one of my classmates had put her key inside the bag that we were using, and I reached in and I felt it and I said, oh, it's a key, it's a Toyota key, because I drove a Toyota for years, and so I had that extra information that it was a Toyota key, which it was. So stereognosis uses the sensory information, but it integrates it with central information from your experience with that object. So pretty cool stuff. But if you lose the sensory information, you can't do that because you don't have it. Also, if you lose the central information, you can't do it either. But there you go. So that's one test you can do with someone on sensory information. So another test, they do sensory nerve conduction studies. A lot of times people who they suspect have carpal tunnel syndrome will have a nerve conduction study. It evaluates the function of peripheral nerves. It does not evaluate the function of the central nervous system. Because large diameter axons normally conduct fastest, nerve conduction studies in an intact nerve measures only the performance of large diameter axons. And you have a stimulating electrode at the distal end. You have a couple different recording sites, and the computer measures the conduction velocity of the nerve. And so in that way they can tell if it's, and it compares it to norms. You can tell if your conduction velocity is compromised in any way. So that's one of the studies that you'll get to test the peripheral nervous system.